All right, everyone, we're going to get started here with the first session. So welcome back. Thanks for making it here on time-ish in the rain. I'm Aaron Johnson. I'm going to chair this first session. And our first speaker of the morning, who drew the short straw for the 9 a.m. slot, will be Grady Williams, talking about some robust sampling-based model predictive control.
All right. Hi, everyone. My name is Grady Williams. I'm with the Georgia Institute of Technology, and I'm presenting our work on robust sampling-based model predictive control with sparse objective information. So our goal in this work is to be able to generate behaviors directly from high-level cost encodings using stochastic model predictive control. And our setup is that we have some system, and from that system we get a dynamics model, and then we have a task, and we encode that task with some cost function. And then we use real-time stochastic optimization to minimize the cost function with respect to the dynamics. So there's no intermediate planning layer here. We're just directly going from costs and dynamics to control inputs. And we've had some success with this paradigm in the past, using sampling-based model predictive control for fast driving. So here are some of our results from ICRA 2017. So this approach works well, but one issue is that it does take some tuning of the cost function to work. And cost function tuning is not really scalable to bigger, more complicated environments. So we'd like to be able to use the same approach, but with simpler, easily composable cost functions. And in this paper, we propose to use cost functions that look like this. So you have a quadratic cost plus sums of weighted indicator functions. And the sums of weighted indicator functions are really nice because they basically just say, did an event happen? And then how bad is it that that event happened? So they're really easy to compose, but they're hard to optimize with because they have zero gradient wherever it exists. So you can't use a gradient-based method. And of course, a sampling-based method can theoretically optimize for these, but in practice, what happens is that you lose the ability to recover from strong disturbances. And here's a video kind of demonstrating what that looks like. So what you're going to see is there's going to be a point mass system, and it's trying to keep, our controller is trying to keep this in the rings. And when there's low noise in the system, it's able to do this quite well. But now, when we really increase the noise in the system, the trajectory wobbles around quite a bit. And since there's no gradient to kind of guide it back towards a good region when it loses a good solution, it eventually diverges. So in order to solve this problem, we propose to combine sampling-based MPC with a tube-based MPC approach. And here's an example of how this works. So we have this car here, and it's on this track, and we have a sampling-based controller, and let's assume it has a good solution for now. And then what's going to happen is it's going to get hit with a big disturbance. And then, again, there's no gradient to kind of help it recover here, and the sampling is kind of locally based around this red line, so we're not going to be able to get a solution guiding us back onto the track. So it looks like we're just kind of dead here. We're not going to be able to recover. So what we do in the tube-based approach is we actually allow the sampling-based controller to ignore that disturbance, and then it just keeps on planning like nothing ever happened. So that's great. That keeps the solution from blowing up. But the issue is, OK, now the controlled state is different from the actual state. So we need to get a second ancillary controller that actually keeps the actual state of the system close to this idealized disturbance-free state. And then, so for the sampling-based control, and the nice thing with this in the tube-based approach is you can show that the difference between the actual and idealized state stays bounded. So for the sampling-based controller, we use model predictive path integral control, and that runs on a GPU. And then we use ILQG for the tracker, and that runs on the CPU. So we get a nice mix of computational resources. And then here's some of our results on this 1/5 scale autonomous racing platform. So the goal here is to go around this track at 9 meters per second. So it has a quadratic cost for achieving the desired speed, and then it just has a weighted indicator cost for staying on the track. So the cost is 0 if it's on the track, and then I think 10,000 if it's off the track, and nothing in between. So 0 gradient wherever it exists. And there's also an additional cost for basically for not sliding out. So trying to keep the slip angle below a desired threshold, and that also is just encoded as a weighted indicator cost. So all of the constraint-related parts of the task are encoded as indicator costs that don't have any useful gradient information. So really sparse information about what the cost is trying to get the vehicle to do. But we're still able to get really nice, robust performance by combining these two methods, so combining sampling-based MPC with tube MPC. In the paper, we demonstrate good performance on some simulated systems and then also on this real 1/5 scale racing platform. And the next step is to look at what kind of theoretical guarantees we can provide in this framework. Thanks, everyone.
All right, thank you, Grady. Next up, we'll have Neil Doshi talking about some contact invariant optimization for some very small legged robots.
Good morning, and thank you for making it out this early. As Aaron mentioned, I'm Neil Doshi, and I'm going to talk to you about contact implicit optimization of locomotion trajectories for a quadrupedal microrobot. The microrobot in question is the Harvard Ambulatory Microrobot, or HAMMER for short. HAMMER is a 1.5-gram quadruped made using laminate manufacturing techniques. This robot has 8 independently actuated degrees of freedom driven by piezoelectric bending actuators. 4 of them control the vertical position of the leg, and 4 of them control the leg's fore-aft position, as you see in the video on the right. HAMMER is able to leverage these degrees of freedom to achieve high-speed locomotion using a variety of gates and control locomotion at both low and high frequencies. However, a lot of these results have been sort of achieved using almost entirely experimental approaches, which requires running hundreds, if not thousands, of trials on this little microrobot. I'm here to talk to you today about a model-based motion planning framework to augment this experimental approach. We phrase the motion planning problem as a contact implicit trajectory optimization, where you minimize some cost function subject to the robot's dynamics and the contact physics. Our approach is to develop a high-fidelity model of this robot and do the computationally intensive motion planning offline. This generates accurate whole-body motion plans that can be tracked on this computationally constrained microrobot using simple controllers. I want to talk to you briefly about the dynamic model of this robot. Here you see one of HAMMER's 4 transmissions. Each transmission is driven by 2 of these actuators that are modeled as a force source in parallel with a linear spring. In addition, each transmission consists of 10 rigid bodies connected by 11 compliant flexures in 3 parallel kinematic chains. So if we assume each one of these flexures moves as a 1 degree of freedom pin joint, this gives us a description of the robot with 76 states and 24 kinematic constraints. In addition, the elastic elements in both the actuators and the flexures result in this 100 hertz natural frequency for each one of these transmissions. And this 100 hertz frequency requires dense sort of temporal sampling, leading to big problems. We model the robot's interaction with the world using the complementarity formulation of contact. On the left, you see a cartoon of the complementarity constraints in the normal direction. These constraints make sure rigid bodies don't interpenetrate and that normal forces only act to push bodies in contact apart. We put the contact physics and the robot dynamics together using this recently developed variational integrator. The second-order integrator gives you a smaller problem for a given accuracy specification than first-order methods, which is great given HAMMER's large state dimension and high-frequency dynamics. We use this method to pre-compute 9 periodic trajectories that ask the robot to move about 10 millimeters per cycle on 3 different surfaces, Teflon, cardstock, and sandpaper, and at 3 different frequencies, 2, 10, and 30 hertz. 10 millimeters may not seem like a lot, but it's near the theoretical stride length for this robot, so we're actually pushing performance. The 3 surfaces represent a wide variety of friction conditions, and the 3 frequencies are sort of different dynamic regimes. Pre-resonance, the Z natural frequencies at 10 hertz, and the roll natural frequencies at 30 hertz. In addition, we also plan and execute a vertical jump of about 1 body height. The robot's performance is evaluated in this motion capture arena you see. We have 5 motion capture cameras that give you the rigid body pose of the robot. In addition, I developed an estimator that fuses these Vicon measurements with custom sensors to give you low latency estimates of the leg position and the body fixed frame. These low latency estimates are used in a PD controller for just tracking the leg position and the body fixed frame, and that's the only control we apply. And so here you see for the 2 hertz gates, the robot's able to accurately track the whole body motion plans despite only using simple joint space PD controllers. This sort of indicates that the dynamic model captures a lot of the salient properties of this robot. In addition, you see good tracking of the desired leg trajectories across most of the 9 gates. On the left, you see that the robot maintains the gate timing predicted by the optimizer for almost everything except for the 30 hertz gates on Teflon. And on the right, you see that the legs are able to, for most of the gates, track the desired trajectory in the body fixed frame. Most importantly, our approach results in a number of performance improvements for this microrobot. Across all the 9 gates we try, the sort of closed loop experiments are 17% faster than the manually tuned gates at the same frequency. In addition, for the 2 and 10 hertz gates, the two columns on the left, we achieve an average velocity of about 9.2 millimeters per cycle. This is comparable to the previous speed record for this robot of about 9.5 millimeters per cycle, achieved using a carefully tuned gate. And so this is across a few different conditions. And finally, we achieve a new speed record of about 11 millimeters per cycle on the 10 hertz gate and cardstock. This is most of the robot's stride length. In addition, we are able to execute this vertical jump of about 10 millimeters, or 80% of the robot's center of mass height. And you can see that the robot sort of accurately tracks the apex height predicted by the optimization. So in conclusion, I showed you this motion planning framework that generates accurate whole-body locomotion plans for this complex micro-robot. We've validated the results on the physical platform and tracked them with simple, sort of computationally cheap controllers. And I think that the number of performance improvements demonstrate that this is a possible alternative to online planning for computationally constrained systems like this micro-robot. Thank you, and you can ask me more questions at my poster.
Thank you, Neil. All right, next we're going to have Taylor Apgar talking about fast online trajectory optimization on Cassie.
Hi, my name's Taylor. I work for Jonathan Hurst at the Dynamic Robotics Laboratory at Oregon State. Today we'll be talking about fast online trajectory optimization and control on our Cassie robot. Along with the simulation results from the paper, we'll also be showing some unpublished work that we are currently doing. So for those of you who don't know Cassie, it's the robot there on the right. It has lightweight legs with springs in them. It doesn't have any perception, so really what we're concerned with is really robust blind locomotion controllers. The user can navigate the robot using some desired end state along with the contact schedule. And this is passed off to an online trajectory optimizer, which uses a reduced order model to find the center mass trajectory along with the footstep locations. These are then sent to a whole body operational space control, which finds the desired motor torques to generate those accelerations. So we use 2 different reduced order models for the online trajectory optimization. In the horizontal direction, we use a linear inverted pendulum. And in the vertical direction, we use 2 actuated springs, 1 per leg. So for the linear inverted pendulum, the optimizer is choosing the footstep locations, the center mass trajectory, and the center pressure. We constrain the center pressure to move linearly in between 2 points during a phase. So by doing this, the center mass dynamics are closed form. So we can just stitch these different phases together using the boundary conditions. So the vertical direction, we use 2 actuated springs, 1 per leg. The optimizer can choose the center mass trajectory along with the spring reference positions. We basically make the spring reference change linearly over a phase, which again causes center mass dynamics to be closed form. And along with that, we also constrain the spring reference to equal the leg length at touchdown and liftoff. And this is because the physical robot has springs in it, so we can't actually apply force at the instant of touchdown, and we don't want force to be stored in the leg as we pick the leg up, otherwise it will oscillate during the swing phase. So we take basically all of these accelerations from the MPC formulation, and in order to calculate the motor torques required, we formulate it as a quadratic program where all of the objectives are quadratic in our open variables, which is the joint accelerations, the motor torques, and the ground reaction forces. The rigid body dynamics formulate the linear equality constraints, and our pyramidal friction and actuator limits are basically just the linear inequality constraints. The operational space controller runs significantly faster than our online trajectory optimizer. So in addition to the feed-forward accelerations that we get from the MPC, we also wrap the trajectories with task-based PD control. So all this works well in simulation. Basically, as you can see here, it recovers from a lot of large disturbances, even by keeping that desired end position fixed. However, when we took all of this and just put it on the robot, it didn't work right away. So we kind of took a step back and simplified the optimization problem. added state estimation, tuned up the operational space control, put a lot of just engineering work into it. And here's some of our more current results on the hardware. As you can see, it had no idea that there was that 8-centimeter step up and step down, but mainly due to the fast online replanning and a lot of the feed forward coming from the operational space control, it's able to handle these large disturbances rather robustly. You can see also, like here, when we violate our friction constraint, it just is able to recover no problem. So we're also adding the Z component back in, and now you can kind of transition nicely from walking gates to more running gates. And this is really because the springs are constrained at the beginning and end of the phase. Really what we want to do is have robust locomotion for outdoors. I think this fast online replanning really works. It's just what is the correct or the best formulation for it. And lastly, I'd like to thank funding and also Agility Robotics for a great robot. Come find us poster session, ask questions, look forward to talk to people. Thanks.
All right, thank you, Taylor. So the last talk in this section will be from Ross Hartley on contact-aided invariant extended Kalman filters, I think also on CASI.
Yeah, so first of all, I want to thank our funding source, Toyota Research Institute, and everybody else in our lab, because it really takes all of us to get a robot like this up and walking. So yeah, one day we really hope to have robots like this walking outdoors and accomplishing various tasks such as firefighting or search and rescue. Here you see Cassie walking around North Campus through a controlled burn that's happening. But really, you need accurate, fast state estimation to be able to accomplish these kind of control algorithms. A common way to do this, to fuse all the sensor measurements together, is an extended Kalman filter. But extended Kalman filtering usually linearizes around the current state estimate. So if you have a poor linearization point, you can have bad filter performance or even potentially divergence. So invariant extended Kalman filtering is a new form of Kalman filtering that works for a special class of systems. So first, you define your state as a matrix Lie group, such as SO3 or SE3. Then if you can show that your dynamics satisfy this special group affine property, then the invariant aerodynamics will be both autonomous and log linear. So essentially, this means that a particular choice of error variables will lead to linear aerodynamics in the Lie algebra of the group. This is important because the linearized error dynamics matrix will not contain the state estimate anymore, but it can still be used to exactly recover the nonlinear aerodynamics along the manifold. So this is some theory citation you can't really see, but developed by Baru and Bonnabel. So we're really taking this theory and using it to develop a contact-aided invariant extended Kalman filter, where we're combining IMU, contact, and encoder information to estimate the base pose and velocity, along with all the current contact positions of a legged robot. We use inertial measurements to predict the base frame movement using a kind of standard strap-down IMU motion model. And then if you assume that your stance foot is pinned to the ground, you can use encoder measurements in forward kinematics to correct this state estimate. So again, we're interested in estimating the 3D orientation, velocity, and position of the IMU and the world frame, along with the position of all contact points in the world frame. We can arrange this state into a matrix Lie group, SEK3, which is essentially the special Euclidean group with extra columns added for the velocity of the IMU and the position of all contact points. We're using the accelerometer and gyroscope measurements to provide inputs to our system dynamics model. We developed a noisy inertial contact motion model where the base pose and velocity is governed by kind of the standard IMU motion model equations. But when we detect contact, we assume that the stance foot is fixed with respect to the world frame. So in other words, the velocity is 0, although we do add some noise to accommodate some potential foot slip. So it is possible we show that this deterministic dynamics function does indeed satisfy that special group affine property. So we have all these nice benefits for the invariant Kalman filtering. Using noisy encoder measurements, we can measure the relative position of the contact frame relative to the base frame through forward kinematics. We can rearrange this into a right invariant observation form, where essentially your measurements are equal to the state inverse times a constant matrix plus noise. And because we can arrange it in this form, we have an additional benefit that the innovation equations will also be autonomous for this filter. Here you can see the final kind of filter equations. The state estimate is propagated through the nonlinear system dynamics and is corrected using matrix multiplication in the Lie group's exponential map. As predicted, the linearized dynamics matrix and measurement matrix, A and H, don't depend on the state estimate and are actually constant in our case. So this is really nice because wrong state estimates won't affect the linearization, and this leads to improved filter convergence properties. So we evaluated this filter. Our filter's on the bottom with a similar quaternion-based extended Kalman filter located on the top using actual CASI experiment walking data. We ran the filters 100 times using the same measurements, noise statistics, initial covariances, but initialized them with random initial orientations and velocity estimates. Our filter, the right invariant extended Kalman filter, converged much more reliably and quickly than the quaternion-based version, often converging within half a second. We have an open source implementation, MATLAB implementation of the filter located on GitHub, and if you want to see some more videos of CASI, you can check out our YouTube links. Unfortunately, they're hidden by the captions, but you can check them out at the poster. So, thank you.
All right, so you can stay out here. Get all the speakers back for the question, panel question section. And then while they're doing that, if you're speaking in the next section, come up here to get mic'd up. All right, so I know it's early, but hopefully you guys were paying attention and have some questions for our speakers. Yes?
I think, okay. One question for Neil.
Yeah.
Can you comment on like how fast your optimization is to find one gate? And does it simplify any dynamics or use like the full dynamics includes like the lag mass and the like a Coriolis term?
Sure. The optimization probably takes a few hours, but we're just doing it on MATLAB, so it's not a particularly smart implementation. And the only simplification I make is sort of assuming that the flexures behave as 1 degree of freedom pin joints. Otherwise, like everything else in terms of the dynamics is in there.
Okay, great. Next question.
Aaron.
Oh, up top. There we go. Yeah.
Let's see. Hello. So this is for the first speaker. Given the optimization framework that you built for the controller, is there a natural way to incorporate metrics that are continuous but are not incorporated there? So for example, like the ride feel or the ride comfort, you know, maximum jerk limits, various other things like that that you might want to put into the cost function, but how would you use that with the particular shape of cost function that you designed?
Yeah, I think so. So the cost function that I showed, there was a quadratic cost, and then there's the weighted indicator functions. And really, the choice of the quadratic cost is just kind of arbitrary. It's really, so it's more like there's terms for kind of the overarching control objective, which in this case was to go fast, but it could be also things like ride, feel, and comfort. And that's kind of in the quadratic portion, or just, that can just be kind of the soft and squishy portion. And then the weighted indicator functions kind of take care of the, and they act like constraints. They're things that you really don't want to violate unless you absolutely have to.
Okay, so that. So you would expect any shape of that initial section of the cost function to not affect the performance of the vehicle in any kind of fundamental way.
Yeah, I think that you could definitely put other things into that first term, and it would be okay.
Okay, great. Is there a green box in the back?
So this question is for Neil. Thank you for the great talk. I had a question regarding how robust do you feel the plans are to things that you you might have gotten wrong. So for example, if the inertia computations or perhaps the coefficient of friction between the robot and the ground, or if you take the robot and put it in grass, do you feel that you'll be relatively robust to these guys, or how would you attack that problem?
So I would say, that probably the right way to go about this is plan with using sort of the best information you have or the best sort of physics model you have, and then you can try to tackle the robustness using control. I've sort of done really simple control because a lot of these more sophisticated methods require a lot of computation, and that seems like a thing that would be difficult to put on this robot. But I'm kind of working right now on trying to think about doing whole body control and things like this without, in a less computationally intensive way. So that's how I would think about robustness.
All right, I think we've got another one upstairs.
Hi, I would like to have a question for the last speaker. So in your RI-EKF, I noticed that the matrices A and H are constant in linearization. So are they guaranteed to be constant, or is it just specific to your problem?
Right, so if you can show that your system dynamics satisfy that group affine property, then that property guarantees that your, for example, your linearized aerodynamics matrix, it won't necessarily be constant, but it will only depend on your system inputs, essentially. But for our case, it happens to be constant, exactly.
Okay, next question. Anyone down here? Yep.
So a question for the first speaker in the session. So would it be possible to add a gradient to the functions, the components that enforce your constraints, like something that guides it back to the track quickly, or why keep them as indicators?
Right. So basically, it's hard to scale. So in our original work we did, we had, so in kind of papers we've published in the past, we've had a gradient guiding it back to the track. And so we've seen kind of several issues with that. One is, actually, we had tried to put multiple vehicles out on the track and have them driving all at the same time. And once you start getting multiple vehicles involved, you start to have kind of collisions of your gradients where it'll either want to go straight through another vehicle, or it'll stop at another vehicle and not go around it. And then also on this bigger track, we've seen with cost functions where you have a gradient, it'll get stuck in local minima very easily and then actually jump the boundary in certain places. So, and of course, all these things, you can think of various tricks to fix these. So for any given situation, you can look at the task and you can look at the cost and you can say, I can fix this if I just change this thing here and there and there. But that doesn't really scale to, what if I want to have 50 vehicles in my environment and I want to be able to drive on any road that someone can imagine? It doesn't really scale to bigger and bigger tasks. So that was the issue that we wanted to address in this paper. But yes, you could include gradients, and in certain cases that is really helpful.
All right, I think we're out of time. And so let's thank the speakers once again. And you can come ask your additional questions at the poster session.